And here we go. So let's get some things in our notes. So first, we have two types of motion so far. We have translational motion, and we're going to have rotational motion. So we want a description of each as well as what causes changes in those motion. So this is a change in the location of the point mass slash center of mass, if we're talking about an extended body. Change in the location of the center of mass with respect to some frame of reference. Whereas this is a change in the orientation of a body about an axis. Now notice here, the axis does not need to be the center of mass. That axis could be constrained wherever. If you think about a door, where's the axis? It's not through the center of mass, it's through the hinges on the side of the door. So with translational motion, what we're going to see is net forces cause changes in translational motion, whereas net torques cause changes in rotational motion. All right, so that means what we need to do is define some things about torque. So here we go. Torque. First off, what's its symbol? It is the Greek lowercase letter t or tau. Okay, it looks like a tilde with a backwards J. I don't know exactly how else to describe that, but there it is. But what is a torque? It is the action of a force that can cause changes in the rotational state of an object or system. So, a couple of things there. First, the action of a force, i.e., torques are not forces. Why is that important? If torques are not forces, you cannot perform an addition of torques and forces. In the same way that we couldn't add apples to bananas earlier in the year, we can't add torques to forces. You can only add things that are like quantities. The next thing about the action of the force is torques require forces. No torque, or the no force, no torque. But let's move on. Can cause. Two implications there. One, not all forces cause torques. We'll come up with a condition in a minute as to when they do. Second, can cause means that when you have torques, not all torques cause changes in the rotational state of the object. You need a net torque to cause changes in the rotational state of the object, because torque is a vector and therefore can cancel out. Now we're going to see torque is going to be another hand thing, which is not going to be fun here on video. We'll make it work, right? For the meantime, we'll talk about torques in terms of clockwise torques and counterclockwise torques, torques that cause things to rotate or change the rotational state in a clockwise fashion or change the rotational state in a counterclockwise fashion. And we'll specify from there. So, when does a force cause a torque? So let's look at our example there. I had my thing or stick hanging from a string. So this was the axis of rotation. And so when I applied a force here, it did not cause a torque. When I applied a force here, it did not cause a torque. When I applied a force here, it did not cause a torque. When I applied a force here or here, depending on which direction, it did not cause a torque. Now, another thing I did was I pushed on this. And so I can draw an X there to represent that push. Notice here that any force that acts through the rotational axis does not cause a torque. Okay? Now, let's just use some common sense here from your physical experience. I know common sense dangerous, but here we go. If I had these three forces and they were all equal, force 1, force 2, force 3, which would cause this thing, that's my stick falling, which would cause this thing to rotate or change its rotational state by the most? Hopefully you said force 1, because it is further out from the rotational axis, right? So I'm going to define a couple of things here in order to help us out. The first thing here is, well, actually, let's do another thing. 4. If I acted force 4, notice it acts at the same point that force 1 does, but it doesn't cause a torque. That's because if I look at this dotted line here, which I call I'm going to call the line of action of the force, it goes through the pivot point and therefore does not cause a torque. Whereas force 1 here, its line of action does not cause, or does cause a torque because its line of action doesn't go through the pivot point. So I want to define some things here as well. From the axis of rotation out to where the force acts, I'm going to call that vector r. And that's a position vector. The longer r is, the greater the torque. That's kind of what we said before. But notice here, r would be the same for force 1 and force 4. So there's a couple of ways of dealing with the torque concept. The first is, notice that force 1 causes a torque, force 4 doesn't. Force 1 is in a different relationship to this r vector than force 4 is. Notice force 1 is perpendicular, force 4 is parallel, or anti-parallel, really. So I need to have a way for multiplying these two things together to get another vector such that I get a 0 thing when they go along the same line, and I get the most when they go perpendicular. Hopefully you'll remember that that means that what torque is a cross product. Because remember, a cross product always yields a vector when you multiply two vectors together. Also about a cross product is maximized in magnitude when the two vectors are perpendicular to each other, and they're 0 when they're along the same line, collinear. So our formal definition for torque is going to be R cross F, and in that order specifically, because remember, the order of the cross product matters. Now, if you remember from our unit before, that means the magnitude of this is going to be the magnitude of R, the magnitude of F, and then it's going to be sine of theta, where theta is the angle between